Hi all. It's been nearly a week that I haven't uploaded any videos. The reason is I was myself thinking of making instead of putting a randomized topic videos, plan to make a series of videos on a specific topic. So while I was pondering on what topic that has to be made for a series of lecture of videos, one topic which was really fascinating me and which was being main core of my research area is optimal control system, which will be very much more appropriate to the modern AI technologies. So, to conduct this series of videos on optimal control systems, that I have chosen two books. One book is based on uh, this optimal control system, written by Subaram Naidu, and the other book is that I will introduce shortly is another classical book, namely Optimal Control Theory by Donald Kirk. So these, based on these two books, I have decided to make a series of videos to uh, shortly and briefly explain you of various topics on optimal control systems. So, what are the contents of these two books? Let us first go through in this video. So, this book has been very nicely written. That I have read so many books. Among these are the two books I felt that this would be highly helpful to make someone new with a minimum basic understanding to understand some kind and applied control systems. So, the content here I am just scrolling here to go to the content page. Yeah, let's start with some basic introductions, and in this video we will see about briefly about what are the things inside the first chapter about the introductions. So this gives about what is classical control system or modern control system, what does mean by optimal control things, what are the essential requirements for to define the problems of optimal control systems, and then briefly it takes us to old back history of how this optimal control systems came with the basic foundations from calculus of variations and optimal control theory, right from Galileo to the modern Kalman system. People during the time of 60s like Kalman and Bellman, and sorry to mention an important key fact, Pontryagin. So, what does then the second chapter says about calculus of variation, which is the foundations for optimal control theory, and how do we formulate this calculation of variations? And the third things about the very classical things called linear quadratic controller. What does mean by linear quadratic controller will be introduced in later videos. And fourth chapter will be about the same thing on linear quadratic controller with an advanced topic like gain margin and phase margin. And the until this chapter will be dealing about the continuous control systems, and the fifth chapter is about the different system like discrete time control systems, and the sixth chapter will be about the calculus of variations based on Pontryagin minimum principles, and the seventh one is some various performance index systems with different constraints. So these are the basic overall view of this chapter, and that based on this content we are going to make a series of videos. And what does this first chapter, let us briefly review in this video. The first chapter starts with a basic introduction that optimization is very essential, blah blah blah. And what does mean by classical conventional control theory? That I hope that you have some minimal basic understanding about that system, single input and single output system of differential equation. That ordinary differential equation can be made by through a transformation called Laplace transform. There are different transform: Fourier transform, Laplace transform. So Laplace transform for ODE can make a transformations. For PDE, that Fourier, then later Laplace can be applied. So this will be introduced, this control diagram where a plant is operating and its output is taken as a feedback to the uh, feedback and compared with the reference, and that generates an error. That error is given to the control, and that control will develop control. value that will be again feedback to the plant until that desired things are being achieved. So this is the basic foundation, and that can be represented in a frequency domain with this equation 1.1.1. And these are some of the basic characteristic of the single input single output systems. But when we coming into multiple output, these systems cannot be analyzed. So we enter into a modern control theory where multiple in multiple output can be given as a modern control theory. That the requirement is to define the system through this ordinary differential equation. This is a state equation, this is an output equations. These are the matrices, and the terminology of state, input, output, and transfer matrices. For nonlinear, this matrices will be introduced into a nonlinear function of state and control variable. And this also G is also will be a nonlinear variable. And this is the modern control things, the same similar to the previous setup. The plant will output an X. Now all these variables will be fed us to the controller, and it will be reference against the reference signal, and that error output will be produced as a control input to the plant. So this have some various stages. The first stage is to define and model the dynamical systems. It can be either a continuous differential system, or it can be a discrete difference algebraic equations. And the second thing is to, once that system is formulated, this is what the diagram is. Once the system is formulated, we have to analyze whether system is have some certain criteria like stability, existence, uniqueness, all those things based on the Lyapunov, for example, a control theory. Once that is been satisfied, then we will be put into some kind of optimization setup where a performance criteria is done, and we can use the principles of triaging, for example, to make a design for that plant. So then optimization plays a key role, considering all these systems of modeling and stability theory. So again, this can be based on two things: static optimization and dynamic optimization. That will be, this is the structure for this general kind of optimization. It can be a geometric approach or algebraic approach. An algebraic approach can be a single or multiple stages. Multiple stages can be based on game theory. This is again the system can be a deterministic or stochastic, and if it is a determinant, it can be a single stage or multiple stages hierarchical way of computing the control, optimal control, that is dynamic, which will be introducing later. Again, the single stage based on it is a static or dynamic, will be using a linear nonlinear programming, or it can be used calculus of variations for defining the control. So optimal control will again try to find an optimal control to travel from the initial state to the final state with certain constraints, and extremizing the performance index. So this has some three important ingredients. One is mathematical descriptions of that and specifying the performance index. And the important thing is to specify the boundary conditions like initial condition and further additional constraint, that what are the minimum and maximum value of the state variables and the control minimum and maximum. So this again the same thing, like defining the plan, defining the performance index, and performance index can be a variable thing. This will again we will see it in the next videos. What are the different types of performance index? There are different sides that we will be seeing. That I'm just here is giving an overall idea about what is optimal control system and what are the constraints. It can be a principal constraint like boundary condition, or it can be a secondary constraints like that maximum, minimum, and maximum limit. And again, we are coming to the formal state is, we are given the state equation like either it's a linear time invariant system or a non-linear system, and given a performance index, final time based on the state variable and based on the control things. uh, how do we compute a set of trajectories within satisfying the constraints, that trajectories will be computed through a set of inputs, control input, which will be an optimal control. So now this has given you overall ideas about that, and then this this historical tool is really very nicely summarized right from the way that Dido has put forward a famous problem called finding and Carthage, and that has led to an idea of calculation of variation. That calculation of variation is nothing but a finding a function which is minimize a functional. So we know that in basic optimization we are in a stage of minimizing a function or maximizing a functions and finding a value which minimizes and maximizes. Here, functional is something similar setup. It's a function of a function, but in order to find the maximum or minimum based on finding a function. So it writes from starter. This setup is from the Poppers, Synodus, but the real thing starts defining a problem called Pachisto Strand problem, and that problem was defined by Galileo, and which was later solved by Bernoulli, Jacob, and John. And these are some attempts has been also done, contribution has been done from Leibniz and Sir Isaac Newton. But Euler has played a very significant role with this calculus of variations. And one of the thing is the joint work of Euler with Lagrange, and that is what the first variation and defining the necessary conditions for the calculus of variations, which is called as Euler-Lagrange equations. And later Lagrange worked on variable n problems, and it introduced adjoint kind of setup, that is what called as Lagrange multiplier method in optimization. And the sufficient conditions, the legendary played a key role, that is called second variations. And Jacobi also has given some nice contributions and led to a legendary Jacobi conditions. Later, Hamilton played an important role in terms of mechanics connecting to optimizations, and he defined a two first order partial differential equation. Then later that introduced into Hamilton Jacobi equations, and this also led to the contributions of other area of optimal control called dynamic program, contributions from Bellman that we will see it later. And also Weierstrass also played an important role and defined certain conditions for the sufficiency, and that has been later developed from Mayer, and through the introductions of adjoining the constraint conditions with the principal performance index. And other key role played by Nesner based on the Gauss theory of geodesics. And Bolsa, Hilbert have done some contributions based on the theory of eigenvalues and eigenfunctions. And again, some in terms of 80s, somewhere, I'm not sure what age, that Mekshan, Hastings, and done. I haven't heard about these names. Again, the second contributions, first we have done about what are the contributions done on calculation variance. Then the second part of the optimal control systems is optimal control theory. Wiener had played a certain role during his contribution during the period of Second World War, defining a linear quadratic controller. Later, Bellman during the 50s, during the Cold War, he defined dynamic programming. Similarly, in USSR, Pontryagin played us very significant contributions of defining what is maximum principle. And also Kalman have uh, have analyzed certain other things along with Bellman, and he has put so many other setup like Kalman filter, a continuous Kalman filter. Then also introduce a matrix Riccati equations. So these are other things like a single input for the frequency domain, multiple. One of the thing which lacks here is the robustness. The frequency domain, all these things are advantages is it we can prove that those controls are robust for a measurement noise and external uncertainty, but these multiple info have very difficult or nearly impossible to define the robustness. So people from UK have put an attention to this, developing some frequency domain analysis for multiple antenna system. Again, this infinity control theory also developed during 80s, which have played a significant role. So these are some of the historical background. But in chapter from chapter 2, as I mentioned, it will be telling you about calculus ability. It's a very key chapter, which will be standalone. Will take two to three videos to explain all basic necessity for calculus of variations, and we'll put it into a kind of pseudocode or MATLAB pseudocode or how to solve those problems. And chapter 3 will be introducing about the linear quadratic regulator. And chapter 4 also will be an advancement of a linear quadratic regulator. Linear quadratic regulator is nothing but the performance will be a quadratic function, and the state equation will be a linear state equation defined by the matrices. So the fifth chapter is for the discrete control systems, and Pontryagin principle is along with the calculus of variations will be defined in chapter uh, 6. And also the other part of the things like dynamic programming also will be introduced, and that dynamic programming giving a similar what we are calculus of variation giving Euler Lagrange equation. Here the Hamilton Jacobi Bellman equations will be introduced, and chapter 7 will give you a special performance index which will give you a special topics for control constraints like time control, fuel control, energy control will be briefly described. And this chapter will give you overall ideas of what is optimal control systems, and that can be foundations for the right now the fancy topics like reinforcement learning. So along with this book also will be go through will we see parallelly, and wherever the topics are similar we will introduce the topics from here in this chapter, this book and that book. This book also a similar thing that it has some 5 chapters, and it is very well nicely written, and these are the things describing the system same like that. But that chapter starts with that book starts with calculus of variance. Okay, this book starts with dynamic programming. Everything has kind of advantages and disadvantages, how the book is been nicely written, and on what purpose it is being written. But both books are easily standalone for followable book and easily readable book. So these are the topics that has been covered here. The chapter starts with dynamic program. Later, once the dynamic programming concepts are understand with pseudocode, then the calculus of variations been introduced, and the Pontryagin minimum principles is introduced. Once this been understood properly, then there are two ways of solving the optimal control. One is direct method and indirect method. One is like building equations and so on, discretizing and solving, or we are discretizing the thing and later we are solving that one. So how we can go through that will be introduced in this one. It's called as like a 2-point boundary value problem. So all these terminologies will be slowly can be understood once that these concepts are introduced hierarchically. So these are the things. What are the inside those things? The same thing that what we have covered in that book in a different structure and different way of explanation, and some of the additional things like this iterative techniques is little bit additionally given in this book compared to that book. But both are nicely written book and standalone can be read and understood the optimal control system. So here same thing like the classical control theory have some deficiency, so it has become necessity for multiple especially not especially it like for example for space altitude optimizations for minimal fuel expenditures. So single output frequency domain have some certain limitations. So it also says about what is a control signal means it's to satisfy certain constraint at the same time to minimize a maximum performance criterion and problem formulation. The important thing is I personally understood is well defining an optimization problem from the real world. If you are making a mathematical formulation of the real world optimization one, that itself will be well enough to solve the problem. So that is one of the key that has been mentioned here. So a problem well put is a problem half solved. So here there is about the mathematical descriptions, and the mathematical description in terms of ordinary differential equations. These are the state variables, and these are the control variables, and so it can be written in a vector and matrix form. And this is an differential equations. It's a non-linear function of state variable and control variable, and this has given some examples, not necessary. And important definition like a set of control input is termed as a control history or a simply control. A set of state variables in different time step or history of state is can be as a state trajectory. and this will be introduced interchangeably during this whole book. And the function, the value of a function, and what is mathematical model, what are the constraints, these are the essential requirements like what he has been made, the boundary conditions. Hope we'll see all these things in the later chapter, what is mean by admissibility and what is mean by control history, what does mean by admissible function, and what means by admissible trajectory, uh, what is by admissible control. So this admissibility is a key concept here, which instead of searching through the whole space, it constrains the space where that has to be searched, that control, optimal control has to be searched. So that we will slowly introduce, because instead of whole space, this is an admissibility area where that really the optimal control lies. So these are the optimal control. It has been defined. Defining the optimal control is to find admissible control and to find admissible trajectory, which minimize this criterion is said to be called as an optimal control and optimal trajectory. Unfortunately, whether this optimal control and optimal trajectory exists or not, we cannot be proved. Rather than this, most of the books or most of the theories are trying to identify instead of finding out whether they existence or not. They attempt to find an optimal control rather than try to prove that one exists. But it may not be unique. It's a good thing that it's not unique, because it has a variety of options for the designer to identify what kind of input optimal control is necessary, and based on their additional constraint that has been given, then uniqueness can be identified. So we are trying to seek an absolute minimum, not merely a local minimum. Hopefully, we will all see this. This chapter is that is the main crux of this chapter. It's just try to introduce certain definitions and what are the control optimal control system, like defining a system, performance index, and additional constraints, and whether if that optimal control is expressed in an explicit functional form, then that is called as an optimal policy, which is we see that deep reinforcement learning called termed as an optimal policy, where we try to make a neural network as a function approximator for the control input. So that can be an open loop and closed loop. The open loop means it doesn't that producing the control only depends upon the initial time, and none of the other future times will define what control has to be done. So closed loop is what that every time that feedback will be given and try to find out the optimal control input. That we will introduce that. And the state variable has been introduced, state of a system has been introduced, linear, non-linear, time invariant, time expiring, the output equations also we have defined. If it is a linear, that will be defined by a matrix equation, that output equation and control equations. All those diagrams all been introduced in the previous book. The same thing is overlapping here, and these are some of the matrix theory and defining certain special matrices through this solvability. And important part of this control theory is controllability and observability for the linear systems. Absolutely, whether a system is controllable or not is defined by this matrix. If it is a single control input matrix, there will be a single matrix called n cross n, and that matrix should be a non-singular to define that is a controllability. If controllability is being defined, it means that there exists existence is being defined. And similarly, an observability matrix also is defined here. Then observability is a single output, then it will be that G has to be an n cross n matrix with the non-singular characteristics. So these are some of the properties that I have just mentioned, not gone very deep enough, like a bird's eye view. Hopefully, we will try to see each and every definitions, the ideas, the concept. The main two thing is the calculus of variations. Dynamic programming, then a direct method that producing an adjoint equation and then discretize and solve it, or we discretize first the direct and indirect method and defining 2-point boundary value problem. What are the numerical methods we will be utilizing in this? Hopefully, we'll see in series of lecture videos on optimal control theory based on these two books in the following days. Thank you very much.